and we're going to do some common ion problems. A common ion problem is going to state something like, what will the solubility be of silver sulfate in a solution of 0.1 molar silver nitrate? The presence of other ions is going to reduce the solubility. So if you were a person, and thank goodness we have these people out there who worked in a hazardous wastewater facility or worked in a water treatment facility, it would be your job to understand common ion problems and slightly soluble salts. Because believe it or not, there's lots of salts, lots of ions besides what we talked about before, like lead and mercury. We know we don't want in our groundwater system, so we would want to find an ion that likes to precipitate with them and do selective precipitation. And I know it's troubling to hear, but we don't really ever get 100% of the ions out. So think about it. If you lived in Flint, Michigan, you probably wouldn't have fresh water even to this day. They're still struggling with that. So take a second to appreciate how lucky we are with our water around here. So this is how silver sulfate dissolves. They gave us the KSP of 1.2 times 10 to the minus 5. If I wanted to know what the solubility was in just plain water, we know that KSP is equal to 4x to the third, which is equal to 1.2 times 10 to the minus 5. If I solved for x, I would get 1.44 times 10 to the minus 2. That's in plain water. That's how many ions or how many formula units will dissolve into ions. So in solution of, if I started with pure water, the solution would have a concentration of 1.44 times 10 to the minus 2 moles of silver sulfate per liter of solution. But this problem tells me that I'm going to start with not pure water, but I have a solution of 0.10 molar silver nitrate. So you got to figure out what the common ion is. Obviously, the common ion in this case is silver. All nitrate salts are soluble, so it's never going to be nitrate. Forming the solid, that is. So we still don't care about the solid. Concentration of solids is considered to be constant, so that's never part of this problem. In this case, we have 0.10 molar. So common ion problems are problems that don't start with 0 of one of the ions. We're still going to get some silver dissolving and some sulfate dissolving. At equilibrium, these will be the concentrations. So my KSP is not going to be as straightforward as it was before. It's going to be the concentration of silver ions squared times the concentration of sulfate ions squared. For silver, I'm going to replace the concentration with my expression that I solved for in my ice chart. I'm going to replace sulfate with this expression. And it's still going to equal my KSP, which is 1.2 times 10 to the minus 5. Let's look at this. In this particular case, I can say to myself, wow, look at how small KSP is and how slightly soluble it is. Compared to 0.1 with sig figs, this is going to be a minimal contribution. So just like we did with weak acids and weak bases, we're going to say, I'm just going to ignore the contribution to make it an easier problem. We only ignore the contribution to make it an easier problem if we're given KSP and we're solving for X. You guys have fancy schmancy calculators. You could probably figure out how to do it. But for us, we're going to recognize that this makes a very difficult problem, easy to solve, and within sig figs, it doesn't change my answer. So, KSP, we're going to solve for X in this case, is 1.2 times 10 to the minus third. So if you notice up here, this was the solubility without any other ions in solution. The solubility has gone down. This is how many moles of silver sulfate will dissolve in 1 liter of solution. Notice the solubility has gone down from 1.44 times 10 to the minus 2 to 1.2 times 10 to the minus 3. Let's do another one with the same salt that has a different common ion. Believe it or not, you'll get to the point where you don't have to do the ice charts, that you'll understand what's going on. This time, my common ion is the silver sulfate is going to be dissolved in a solution that is 0.20 molar potassium sulfate. Potassium is a spectator ion. This time the common ion is the sulfate ion. Remember, we put molarity in ice charts, not moles. This is plus 2x, and this is plus x. So at equilibrium, my concentration of silver ions will be 2x. My concentration of sulfate ions will be 0.20 because the sulfate ions aren't going anywhere, plus x. So let's plug this into my KSP expression. Replacing my concentration brackets with what I solved for. This time this is 2x squared, and this guy is 0.2 plus x, but we're going to say this is going to be so small that I'm going to ignore it. So it's not going to be 0.2 plus x, we're just going to use 0.2. My KSP for silver sulfate is still going to be 1.2 times 10 to the minus 5. So this is 4x squared times 0.2. Solving for x, I will get an answer of 3.87 times 10 to the minus 3 molar. So you'll see that the concentration decreased. In pure water, it was 1.44 times 10 to the minus 2. In a solution of potassium sulfate, it's 3.87 times 10 to the minus 3. Okay, I'm going to do one more for you, and then you guys are going to try it. They could also give you the solubility. So they're telling me I have CE IO3 as a slightly soluble salt. It's going to fall apart into one piece of Ce3+, 3 pieces of the iodate ion, like such. Now, it's going to tell you the solubility, which is how many pieces of CeIO3 are going to dissolve, is 4.4 times 10 to the minus 11. That's how many moles of CeIO3 will dissolve in 1 liter of solution. So basically, they're giving you the value for X. They're asking how much will dissolve in a 0.20 molar solution of KiO3. Obviously, potassium's my spectator ion again, and my common ion is the iodate ion. Let's go through here. Solids we don't care about. We're going to get 1 piece of him. Like such. So I'll go down to my KSP and write my expression. So now we're going to plug in what we know. This time, we know what X is. So we don't have to ignore the plus 3X. That doesn't save us really any time. That's just being lazy. So for KSP, which is given to us, oh no, we're solving for KSP, and X is given to us. So we're going to place this with X, and this with 0.20 plus 3X cubed. So the value for X is 4.4 times 10 to the minus 11. And this is 0.2 plus 3 times 4.4 times 10 to the minus 11. Do you guys get why we're not ignoring X in this circumstance? I mean, the only time you don't ignore X is when we're solving for KSP. So in my calculator, I start at 4.4 times 10 to the minus 11 times 3. I press enter. Plus 0.2, press enter. Raise it to the 3rd power, press enter. Then I multiply by 4.4 times 10 to the minus 11. And I get a KSP of 3.52 times 10 to the minus 13. So you get there's 2 possibilities. You could be solving for KSP. You could be solving for the solubility. If you're solving for KSP and you're given the solubility, you don't need to ignore X because X is the solubility. If you don't know the solubility, but you are given the KSP, that's when you can ignore X.